Hi, welcome to my talk, Building Data-Driven Applications with Go. My name is Felix. I'm running the engineering teams at a company called KI Labs. We mostly work on software and data engineering projects, and Golang is part of our technical stacks. And today I'm going to talk about how you can use Golang to build data-intensive applications. So why data intensive? I didn't want to write down the overused data is the new oil claim. However, it is fact that we produce more and more data. You can check out a visualization called Data Never Sleeps in its current version 7. It contains some impressive statements such as by 2020 there will be 40 times more bytes of data than there are stars in the observable universe. And the picture shows other interesting examples on how much data we generate every minute. So consequently, we need ways in our applications to deal with larger amounts of data. Now, a lot of big tech companies have released their internal tooling to deal with those massive data sets as open source, and this has led to a vast big data ecosystem that is getting more and more complex and also confusing. But chances are you're not processing in your applications data at that scale. So in this talk, I'd like to show you how to solve, let's say, 80% of your data problems with simpler tooling. So we're not going to talk about Hadoop or running Go on Kubernetes. So Go itself has a couple of built-in language features that make it very suitable to efficiently process data. And when we talk about processing data, we often talk about data pipelines. So how could you define a data pipeline? We could define it as the process that takes input data through a series of transformation stages, producing data as output. And then in the entire data world, we have a special type of data pipelines. It's called machine learning pipelines. And this we could define as the process that takes data and code as input and produces a trained ML model as the output. Let's first have a look at what the typical main building blocks of a data architecture are. So first we need to somehow ingest data from our sources into the system. Then we often store the raw data. Then we process it, then we might store it again, maybe this time in some clean or optimized format, and finally serve it typically through an API endpoint or PubSub. This basically picture more or less also maps to the well-known concept of ETL, extract, transform, load. And in this talk, we mostly focus on the ingest and process parts. So if you look at the data flow in a typical pipeline setup, it roughly looks like this. So raw data in different formats is ingested, often through a queuing system. Then it ends up in a stream processor, or it ends up on typically HDFS, which is the Hadoop file system, or maybe an object storage such as S3. Then, depending on whether you are dealing more with streaming data or batch data, after processing it, it goes back maybe to the queue again, or is processed and picked up by some batch jobs. A final destination is then often target storage, persistent storage optimized for certain data types. This could be relational data, time series data, document key value stores, and so on. And from there, then we access it and serve it to different clients. So the example I explained before would already involve a lot of expensive data tooling. But what is really the simplest thing you could do to set up a data pipeline that can still process a reasonable amount of data? Here we can see an example from Martin Kleppmann's book, Designing Data-Intensive Applications. which is, by the way, a great book. If you want to know more about that topic, you should read it. So he gave this example, and there we connect simple Unix tools through pipes. So as you can see, we have awk that reads an access log file, then we extract some part of that log file, we sort it, we determine the counts that for the unique values, then we numerically reverse sort it again and use five items. And this looks very simple, but it's actually more than a poor man's solution. So first off, it uses this Unix philosophy, so we compose small programs that do one thing well, which gives you a lot of flexibility. And also, it actually is able to handle large data sets, because if the data wouldn't fit into RAM, it would automatically spill to disk and also run in parallel across multiple cores. So it's actually quite powerful. On the other hand, tools like awk, for instance, can get really also awkward in terms of their syntax. I don't know if you're aware that awk is actually Turing complete language. And I'd argue that anything more complex than the simple example I showed before would involve for most of us a lot of Googling, trial and error, and so on, so to actually achieve what you're after. And what I showed earlier, piping these Unix tools together, has often been loosely referred to as Taco Bell programming. Which then finally brings me to Go and its standard library and built-in language concepts such as channels and goroutines, to realize basically what we would call advanced Taco Bell programming. So we can use goroutines and offload work to multiple CPU cores and benefit from parallel processing. And we can use channels to communicate between those processing stages and construct data flow pipelines. And then in the end, you can all easily deploy it in a single binary without any data infrastructure nightmares. However, even with a nice language and runtime, things are unfortunately not so straightforward when dealing with large data sets. So one of the main challenges is memory, meaning whenever your working set, which is the data you're currently processing in memory, is bigger than the available memory on the machine, you obviously run into out-of-memory situations. And this is bad because then you need to use disk I/O, which is an order of magnitude slower. And you could also run, of course, out of disk space and so on. But there are a couple of techniques how you can address this challenge. So first, instead of adding RAM or spinning up an expensive big data cluster, the first technique is compressing your data. And here we are not talking about zipping it and unzipping it, but actually compression in terms of how data is represented in memory. A very simple example could be to store some values not as strings, but as different data types, such as booleans or bits, such as 0 and 1s. The second technique is that you can chunk data, which is you cut the data in logical pieces and process them one by one in parallel. So you don't load the entire data set into memory. You might know this principle as MapReduce, which is basically doing this in a distributed fashion. So how does MapReduce work conceptually? Using the example of counting books in a bookshelf, it works like you count up the shelf 1, I count up shelf 2, and the more people we get, the faster this process would go. And then we reduce, which is we all get together and add up our individual counts. The third technique I'd like to mention here is indexing. This is common practice, for instance, when using log files and log rotation. You usually put all data for a certain time period into a logical file. and then you maintain an index, which is sort of a summary to point to the individual files, and then you just load them when actually needed. So now we really move to some Go code and examples that show you how to build simple data flow systems. And the first concept here I'd like to mention is generators. So we could define a generator as a function that returns a sequence of values through a channel. We could also refer to this as a producer-only module. And use cases for a generator could be streaming numbers, loading a file, reading from a database, scraping the web, and so on. And for the purpose of these examples, we just type this channel to an integer, but you could, of course, use any custom data structures as well. The second abstraction is a processor, which we define as a function that takes a channel and returns a sequence of values through a channel. Use cases here are any sort of number crunching, data aggregation, deduplication, filtering, validation, and so on. So everything what you basically do in terms of transformation and processing. And finally, the third building block of our data flow system is a consumer, which is just a function here that takes a channel. And in the consumer, we can consume the channel, which is we could print the sequence, save the data somehow, etc. Now, when setting up these data flow functions, what you can do is creating functions that return the type definitions, which are themselves defined as functions. And you may know this pattern from setting up HTTP handlers and middleware for server applications. What is it useful for? So, for instance, you could further customize these inner functions while still returning the expected type, which is generator in this case. And here in this example, we just have parameters that we pass to this outer function that we could then use in the inner function. One example for our first pipeline is a simple number generator. So here in the inner function, as you can see, we create an output channel. And then in the Go routine, we write numbers that were passed in the outer function to number generator. And we write them basically to this output channel. And when the loop is done, we properly close the channel, and the inner function returns this output channel to stick to our basically type definition. Next is the processor. Here we do something similar, except the inner function ranges over the passed channel. Then we do a simple calculation, squaring the numbers in that case, write again to the output channel, and also again close it when it's done. And finally return this channel. The consumer then just takes the channel, and here it has a forever loop. Basically, it reads it receives the value from the channel, checks if the channel is still open, it can actually be received, and if yes, we print it. If not, we exit. Next, we can construct this pipeline and actually run it. So what we do here is we call our creator functions, nest them so that the channels can get passed to these functions, and then we run it. So we have a print consumer that accepts the channel from square processor, which again accepts the channel from number generator. And in this case, since we just square the numbers, we would just see 2, 4, and the other numbers that we pass to number generator. We can get a bit more advanced by implementing Some of the memory techniques I showed earlier, for instance, chunking and indexing. So we construct a pipeline that uses fan-in, fan-out patterns to basically divide up the processing work, and then later merge these channels back before the consumer iterates over it. And this is what it could look like in code using basically the example of 2 log files passed to one processor each. And then we have a new function, log aggregator, that takes a variable number of channels and merges them into one channel. So there are many options basically how you can set up these generator and processor functions to compose the data flow depending on your needs. What I just explained is also often called multiplexing or merging. So the aggregator, as I said, takes a variable number of channels and returns a maybe buffered output channel. And multiplexing, we could then say, is ranging over all the input channels and internally using weight groups to close the output channel when all inner goroutines writing to this output channel are done. And the code for this, or part of the code, could look like this. We use the weight group from the sync package, and then in the outer for loop we range over the channels. We add to the weight group, start the goroutine. The goroutine gets this channel passed and then internally ranges over it and writes all values into a single output channel. One important topic when linking together pipeline stages is making sure not to block channels or run into deadlocks. And there are a couple of strategies that help you to address that. One is to make sure that each basically stage that owns a channel is also responsible for closing that channel. So imagine a situation where a downstream processor would run into an error and could not receive the value from the upstream channel. This will basically block the sender. And what you can do here is you could use buffers to avoid that, but it's a bit tricky to get them right in terms of what does your buffer size need to be and so on. In any case, what you should do is have a way of shutting down and stopping the entire pipeline. And one way to achieve that is by creating a done channel and passing that done channel to all functions. And then you can use a select statement which ensures basically that this ranging over the channel continues either when the send operation, right, with your processed values succeeds, or when value on the done channel is received, in which case the loop will exit and the channel is finally closed. So you might also actually not want to explicitly close the channels at some point, but rather continuously consume a stream of values and process them. And when we talk about real-time streaming, what we usually actually mean is processing at very frequent update intervals. And one very simple way to achieve this through a generator is introducing an artificial delay, in this example here, just through a sleep call. So you can see we create the output channel, a random number generator, and then have a loop, and this loop contains basically a sleep call. And what we don't have is the close statement for the channel, so it would continuously sort of stream the data into this channel. If you then have streams with high update frequencies, you might wish to rate limit them, for instance, to avoid quota exceeding or resource exhaustion. And what you can do then is you can add another processor that limits this processing to a defined rate, for instance, n operations per second. So in your processor here, what we do is we create another channel called throttle, and then we use a ticker to write values into the throttle channel on each tick. And this tick is basically defined through the rate that you set. Then later, in the bottom part here, when ranging over the input channel, you first receive the value from the throttle channel before writing to the output. And this receiving operation here at throttle would of course block according to the ticker rate. And this is how you can throttle the entire thing. So what I've presented here so far may be sufficient for simple pipelines and processing needs, but your use cases might be more complex. So maybe you want to consume data from your existing source systems or queues, or distribute the computation across multiple machines. And for anything beyond simple pipelines, there are a couple of open source projects that I wanted to point out. One is called Benthos. It's a stream processor. It implements a concept of sources and sinks and supports actions, transformations, filters, and so on. We will have a look at it later. And then another one is called Automi. It's a stream processing API. It implements similar concepts to what I just presented. They call it emitter, operation, and collector. It's basically an abstraction on top of channels, and but it's very early stages. And then we have BigSlice, which is an ad hoc cluster processing framework, not strictly streaming, but you can distribute computation across multiple nodes, similar to, if you're familiar with Spark, what that does. But it's basically serverless, and it's much easier to deploy and use. So one of the concepts that Benthos implements is that of sources and sinks. And other terminology in use is producers, consumers, or inputs, outputs, but it's all basically the same thing. Now, depending on your existing infrastructure, you may have heterogeneous data sources and target systems. So it'd be ideal if you could somehow connect them in a flexible way and just customize the processing logic. And while you could achieve that with the techniques that I showed, you may wish to have a more robust solution that you can configure, and that also comes already with connectors for popular data components. So as mentioned, Benthos is one such solution. It has a number of benefits. So it directly links inputs to outputs and also supports the concept of acknowledgements. It also has optional buffering features. Then it supports resilient and customizable processing logic. You also have some convenience features that you can add to your processes, for instance, some JSON queries. And it's in general well documented. You can configure it, and it's also used in some production systems. So how does that work under the hood? There is a very interesting presentation from the main developer on Benthos, and he presents the inner workings through simplified code snippets. Here you can see, for instance, that reading is not directly done from the input channel, but from a queue abstraction. And writes into the channel are done using another abstraction called here a transaction that basically enables communication back from the sinks to the source systems via a response channel. And this is how they implement acknowledgements, which means making sure that the data was really committed to the target systems. Customizing the processing logic is also quite straightforward, as you can see here. So after reading the configuration here, a processor is added, and a processor is just a function implicitly conforming to their processing interface. And speaking of configuration, you can describe that in a YAML or JSON file and set up your inputs and outputs. Here, for instance, a Kafka broker is configured, meaning that you want to consume data from a certain Kafka topic. And then processes in Benthos are handled in a separate layer. And you can configure how many of those processes you want and what they should do. And then you configure your targets, which could be files, a database, and so on. In this case, it's just another Kafka topic where the data should end up after processing. So some final data recommendations. So use Go, obviously, and also maybe try to play around a bit with some of the data flow programming techniques that I showed. You should also stay lean and check if you really need these big data toolings, since you should be aware that there are both infrastructure complexities and runtime overheads involved. So, for instance, splitting data sets, serializing them, sending them over the network to do this distributed computation is quite an expensive process. And so, in generally, just critically evaluate and maybe run some tests and spikes before. There are actually many stories where people wanted to process a decent amount of data and then early used Spark, which somehow took 15 minutes to process the data set, plus the ceremony of launching the cluster and tearing it down again, while directly querying the relational database would have maybe taken only a fraction of a second. So to recap, in this talk we looked at basic building blocks of a data pipeline and some of the challenges when processing large data sets. Then we covered some general techniques to work with data in memory. We looked at how to construct simple data flow systems using goroutines and channels. And finally, we looked at more advanced open source tooling to set up more flexible and scalable pipelines. So my last slide, I have also a couple of links that you can check out later to learn more about what I've presented. And I think that's all I have. Thank you. And maybe some questions.
All right, we still have plenty of time for Q&A, so if you got questions, just raise your hand, I'll get you a mic. Okay, I already see one over there.
Hi, my name is Ilya. Thank you for the talk.
Hi.
The question is, for example, if I have several pipelines and by some reason I want to control the throughput of each pipeline, how can I do that on this low level using Go and goroutines, channels, and so on? So if I want, let's say, I have pipeline that working with database, and for some reason I want to spawn more workers or less or something like that. How could be easier to configure it on flight in the runtime?
So one thing you can do is what I showed is that if you use these processing functions, for example, they use internally goroutines, and you could of course spin up more of those. Something what I did manually in this example, when I then, before I merged them back, so this sort of MapReduce principle, then you can have other, if you want to control, I understood throughput and so on more, you could also have custom processors that sort of limit the flow of data. And if you use something like Benthos, for example, there you can exactly configure how many processors you want to have and so on, both on the consumer side and also when you basically extract it from the source systems.
But if I want to change this number on flight, how to better do that? Kind of HTTP handler with a callback, or maybe maybe, I don't know, dynamically read and updated configuration file?
Well, I mean, so basically, I guess in production, you want to do this based on some metrics that you collect and that you monitor. Benthos, for example, as far as I know, can be updated live. So whenever they have a management API there, where you can change this configuration and it would update in real time. And then maybe you could connect it to some sort of metrics that you collect.
Okay, thanks.
Any more questions?
Here is one.
Hello, thank you for the talk. One of the problems I kind of encounter with using like the simple stuff is like avoiding bottlenecks, like waiting on channels that like the consumer is not consuming enough and the producers are like, what are the patterns that you recommend like solving this kind of problems? Like one case is like rate limiting, and what are other kinds of patterns would you recommend for that?
So you mean in order to control the rate of data?
The rate of data, so you don't have bottlenecks like if the
Well, so what is typically done is to introduce buffers then into this, even though it's interesting, the main developer of Benthos says don't use buffers at all, because most of the time you don't need them, but there might be cases where you need them, and then of course if you have producers that are faster than your consumers, you can fill a buffer and consume from there. And then it also depends on how many CPU cores, what machines do you have available, and this is how you then configure your processing logic. I think there is no single answer to that question. It's a very complex topic.
Thank you very much.
Thanks for the talk. Small question, what do you think, would it be a more scalable approach if you just use normal queue, for example, RabbitMQ instead of channels, and then you can just orchestrate number of consumers? Yeah, just want your opinion.
Sure. I mean, yeah, the point I wanted to make here is a bit, since whenever you use something like RabbitMQ, Kafka, and so on, it introduces some complexity. It's a distributed system. Many things need to be known, configured, and so on. But yeah, often people do this, maybe sometimes too early when you develop an application, that developers often throw message queues maybe too early. And the point I wanted to make is that you can get quite far with simple tooling, command line tooling even, and if you use Go, then you also have some nice built-in primitives how you can construct these data pipelines. But inherently, of course, there is nothing wrong with using a message queue if you need that. But maybe you can think about if you really need it, and if you cannot solve it, also with the built-in things that you have in the language.
No more questions? 5, 4, 3, 2, 1. All right, offer one last round of applause.